Okay, so let's move on to our second speaker and last speaker for the morning. It's a pleasure to have Subhojoy Gupta from IIS, I believe, right? Giving a talk on harmonic maps and framed SL2C representations.
Okay, thanks. I thank the organizers for the invitation to speak at this wonderful conference. Learned quite a bit. I'm also grateful that I have this opportunity to speak at this blackboard here. So I'll be talking about harmonic maps. This is joint work with my former PhD student, Mazzeo, who's around. Let me start with a little bit of a context. So in the 1980s, Donaldson proved following theorem. So here, X for him was a closed compact Riemann surface. So it's a Riemann surface of genus at least 2. And the PSL2C representation, which is a representation for the fundamental group of the surface to PSL2C, is irreducible. Irreducible representation. Then he proved that there exists a row equivariant harmonic map from the universal cover, I'll call it H, from the universal cover of X to hyperbolic 3 space. Okay, so here, just to spell things out, so row equivariant, this means that the action by deck translations, the fundamental group transported to action by isometries, so PSL2C acts by isometries on H3. So this is what means. And of course, this is also unique. So he proved this theorem. I should also say what harmonic is, although it's not, maybe it's not for this conference, but I'll just do it quickly. So this harmonic map here is a critical point of this energy functional that we've already seen, L2 norm of the derivative. And as was observed last week a few times, that this right-hand side is actually independent of the metric sigma on the domain, but it's only depends on the conformal class. So that's why in the theorem here, we only care about the Riemann surface structure. So that's X is a point in Teichmuller space. Okay, sorry, this is a square here. Now, so this quantity, this integrand here is what I'll call the energy density. And it'll show up a few times. Right. And also I should point out that for those who are more familiar with that viewpoint, this theorem is really the existence of a harmonic section to a certain bundle. So it's the harmonic section of a bundle which I won't describe. It's just associated to this representation rho. It's a flat H3 bundle over the Riemann surface. And from this point of view, this was generalized by Corlett to the context of flat G bundles, so representations, surface group representations into a complex semi-simple group G. And this is really one of the directions in the non-abelian Hodge correspondence, which has already appeared in this conference. So the proof, both Donaldson and Corlett, this uses the harmonic map heat flow. So I'll say a little bit about that because that's the tool we also use. So we've already been introduced last week in Franz's lectures to tension field. So it's a recall here that if you look at the first variation of the energy functional, so here FT is a sort of family of maps. Look at the first, you can look at the derivative at time t equals 0. You get an integral that looks like this. It's a sort of a inner product of the tension field with the variational vector field. And this quantity here is the tension field. Okay, so this trace of nabla df. And this is what will govern this flow. Okay, so what does this flow look like? Well, solve for it's a partial differential equation where it's x, so it's defined positive. Sorry? Yeah, right. So right. So now I'm calling the solution now U. All right. So so this was just a sort of functional. Yeah, maybe I should have used F, but let me just stick to. So this is the so you have the initial condition, and then you have a flow governed by this tension field. You can think of this as the gradient flow in the space of maps. So you're trying to minimize energy the fastest. So this, as you might already know, is pioneered by Eales and Sampson, who considered the case where you have compact Riemannian manifolds. Where n is as sectional curvatures all non-positive. I'll just abbreviate it saying non-positively curved. And so then if you start with an initial map from M to N, so let me just say for an initial map like this, this PDE has a solution for all time. So this T parameter here. So the solution, so a long time solution exists. And moreover, this UTs converge to a harmonic map. And now, I won't say much more about the proof, but let me just point out what a key step that will play a role in this an analog that we'll be doing is that along the way, this energy density that we defined there remains bounded. Okay, so this is sort of a uniformly bounded over time. Okay, this was one of the steps along the way. Now, in Donaldson's proof, you're not in the compact setting. Well, your domain is still okay because it's, after all, the universal cover of a compact manifold, but the target is non-compact. It's H3. So, so Donaldson needed to prove a little bit more. So the worry is that along the flow, the maps would just drift out to infinity in H3 and never converge. And so you need to show that at least the 1 point converges. So needed to prove a 1 point convergence result. So let me tell you briefly how that goes. So in other words, okay, so let me just say, you want to prove that if you pick a base point x naught, this ut of x naught remains in a compact set. H3. Okay, so I'm going to think of H3 in the ball model. A little bit, this is my H3. So it doesn't go sort of drift off to the boundary at infinity. And so here's where one uses the hypothesis that rho is irreducible. So this implies that if you take any boundary point, this is the boundary to infinity, you can think of it as CP1. So then there exists some gamma that moves it somewhere else. So there's no global fixed point because it's irreducible. So there's some gamma such that rho gamma of xi is not xi. Maybe it lands somewhere else. Right? So this implies that if you're very close to this point xi, let me just try to. You lie in a neighborhood. So if this point ut of x naught lies in a neighborhood n that I've shaded here, right? So then the distance h3 between ut of x naught and rho of gamma of ut of x naught is very large. Okay, so it goes to some other neighborhood here, but if you're sort of close to enough to the boundary, the geometry of H3 is such that this distance between this and its translate would be very large. Okay, however, we have this energy density bound, right? So this uniform bound in energy density, this actually implies that the distance in H3 between ut of x naught and ut of gamma of x naught is bounded. Yeah, I've sort of used constant c here. This is precisely this, right? With the rho equivariance of UTs, which is preserved along the flow. And so this contradicts the fact that we had assumed that UT of x naught is in this small neighborhood around xi. Okay, and so if you can do the psi was arbitrary, and this actually sort of completes the proof because you can now sort of so this doesn't belong to this, and so you can it actually avoids the neighborhood of the whole boundary. Okay, so and you get 1 point convergence. Now, today we'll be talking about sort of an analog of this theorem in the setting where x is going to be a punctured Riemann surface, which, and I'll explain these terms, it will be a conformal completion of a point in what's called enhanced Teichmuller space. My domain will be non-compact, and our representation rho would be what's called a framed PSL2C representation. Okay. Now let me sort of introduce these now. So all this, so maybe this is sort of the second part. So all this comes up in the theory of marked and bordered surfaces. This is kind of introduced in the work of Fock and Goncharov. In this seminal paper on moduli spaces of local systems. And so let me explain what the setup is. So here a marked and bordered surface is is a pair SM where S is a compact surface and M is a set of marked points. Okay, so set of marked points on S. Let me just draw a picture. So maybe I have one genus, and let's say I have a boundary component, and maybe the marked points are things which some of them lie on the boundary, and I'll in fact require that. So let me mention it, so such that at least one mark point on each boundary component. And some might lie in the interior. In fact, the interior marked points are often, it's useful to keep track of them as a separate subset. So these are the interior points P. Okay, so the ones here. So this is an example of a marked and bordered surface. So I'll also, we'll assume here that we'll kind of rule out a few topologically simple cases so that, so finitely many cases, so we'll assume that if you puncture the surface at these interior punctures, your Euler characteristic is negative. Okay, so we'll kind of have that as an assumption. Now, so given a marked and bordered surface like this, one can actually equip it with a hyperbolic structure in which it looks like this. So the interior points can either be cusps or boundaries, and these boundary points become what are called boundary cusps. Okay? And this the portion here is what is called a crown. Okay, so that's this. So these are hyperbolic surfaces with either cusps or boundaries and geodesic boundary components and crowns. Okay, so so maybe I should say closed boundary. And enhanced Teichmuller space is a space of such hyperbolic structures on this marked and bordered surface. So, so denoted by T plus minus SM. So the space of hyperbolic structures on SM up to the usual equivalence that Charles talked about last week is isometries isotropic to identity. And maybe this won't play a role in my talk, but just for completeness, this plus minus refers to an additional thing, which is like a signing at the closed boundary components. So there's a choice of sign at these closed boundary components like this. So there's a plus or minus, which is like a choice of an orientation of the curve of which part of this the data. All right, so this appears in several contexts in recent years, and I won't get into that, but it has a nice parametrization. It's again a cell and so on. But what I would like to mention now is that this notion of a conformal completion makes it a punctured surface is something that's simple. So the conformal completion of some X, it's I think easier to draw a picture. It's a punctured surface. So this, as it stands, it's an incomplete hyperbolic metric. You can make it a punctured Riemann surface by adding half cylinders, Euclidean half cylinders to these closed boundary components, and half planes along these geodesic boundaries, these lines, geodesic lines that are the boundaries of these, of the crown, okay? And so let me just, so this is denoted by, I'll denote this by x hat. So, so this is obtained by adding Euclidean half planes and half cylinders. But topologically, it's going to be homeomorphic to well, the interior of S with these punctured, so something like this. All right, and conformally, it's in the universal cover. The universal cover is going to be conformally the hyperbolic plane. So here's where this negative Euler characteristic condition lies. And I'll instead of having these double hats here, I'll just denote this space by H. So one can view it. So maybe I should draw a picture somewhere. So one can view this as sort of attaching the universal cover as you take a lift of, you take the universal cover of my point in enhanced diagonal space, which will sort of look like a convex subset of H2. Some of these points I'm drawing are lifts of these cusps, some of them lifts of boundaries, and then there's maybe these some kind of lifts of these crowns. And so this is sort of X tilde, and we kind of attach these Euclidean half planes to each of these boundary geodesic lines. Okay, so that's sort of the picture I'd like you to have in mind for this universal cover of this conformal completion. Okay, so that's the domain. So that's one of the things that will go into our statement of our theorem. Now what's a framed representation? So let me explain that. Also a notion introduced by Fock and Goncharov. So a framed PSL2C representation, and I'll denote that by rho hat. It's again a pair of a representation to PSL2C, the punctured fundamental group of the punctured surface, that conformal completion, and there's a map, which is this is the framing in this context. It's going to be a rho equivariant map defined on this Fairy set. This F infinity is the Fairy set, which is these points, these ideal points in the boundary at infinity of X tilde. You think of as I'm sort of drawing here in yellow. So there's some kind of a pi1 invariant subset on this side. So where subset of the boundary at infinity. So where F infinity, I'll just say the lifts of the marked points. Right? And Fock and Goncharov introduced this in more generality for PSLN, but one of their insights to why one sort of adds this data, the framing to the representations, that the rho equivariant of betas. So maybe I should sort of draw the picture just to clarify. So beta sort of maps these yellow points into CP1. So the yellow points. Well, okay, so there's infinitely many of them. So that's the map, the framing at infinity. Okay, so the fact, this is sort of the reason why they introduced this perhaps is the moduli space of framed PSL2C representations. The algebraically as algebraic variety is quite nice. In fact, it's just complex torus. Okay, so this is, I'll denote that by chi of SM. So it's birational to P star to the E, where this dimension E is a topological quantity. It depends on the topology of SM. It's just the number of edges in an ideal triangulation, of the marked and bordered surface. So here the sort of the vertices are at these marked points. So in the universal cover, such a triangulation will, give a it will give a triangulation up here. So maybe sort of draw a few geodesic lines just to indicate. And the coordinate, the Fock-Gonchar of the C star, the non-zero coordinate associated with each edge is the complex cross ratio of these the images of these four ideal points that you see in the picture adjacent to this edge. Okay, so adjacent to that, the two ideal triangles, and that will have four ideal points, and you look at the complex cross ratio. And this is defined over a Zariski dense set. This is sort of birational isomorphism over here. Okay, and in fact, I should also say that the real and positive points, where these coordinates are sort of positive real numbers, so cross ratios real and positive, is precisely, gives us Fuchsian representations. There's precisely enhanced Teichmuller space. Okay, so this is connection with enhanced Teichmuller space. Okay, so that's the setup. So let me just now state our theorem. So given a point X in enhanced Teichmuller space, and so its conformal completion, X hat, which is a punctured Riemann surface, and given a representation rho hat, this is a framed representation, which is non-degenerate. You can think of this as an analog of irreducible for now, and it's also type preserving. I'll say what that is in a minute. The framed PSL2C representation. Then there exists a rho equivariant harmonic map. I'll call it U this time, from the universal cover of that punctured surface to H3, which is asymptotic to beta. What asymptotic to beta means that is, if you, in the domain, if you go towards one of these yellow points, these points in the fairy set, let's call it X, then the image in this harmonic map, which is inside now in the interior in H3, these will sort of converge to beta of X. So it's asymptotic in that sense. Right, and so here non-degenerate, you can think of non-degenerate as meaning that it's part of this open dense set where these Fock-Gonchar of coordinates are defined. Okay, so this is one way of thinking about it. This is the analog of irreducible, in some sense, but it's not equivalent to it. And type preserving just means that for peripheral elements around cusps, the image on the rows, they map to parabolic elements in PSL2C, and and there's peripheral elements around these cylinder ends corresponding to these closed boundaries. They map to loxodromic elements in PSL2C. So we kind of impose that type-preserving condition. And so that's the existence result. Now, I'll leave some space and talk about uniqueness. But I'll need a bit more for that. Namely, the uniqueness will have to do with the Hopf differentials. So these turn out to be infinite energy harmonic maps. Some of these punctures are blowing out to these crown ends and so on in the target. But what it will have are these Hopf differentials with poles at these punctures. So let me tell you a bit about this relation between Hopf differentials and the behavior of harmonic maps, which we have already seen in Mike Wolf's lectures last week, but this will be a sort of a quick review, perhaps. So recall, first of all, that this is something we've seen several times last week. So the Hopf differential is, so given a harmonic map, call it H, from a surface to some Riemannian manifold as a target. Here, of course, it'll be H3, but let me just state it more generally. So given a harmonic map like this, its Hopf differential, which I'll denote by Hopf of H, is given by the pullback of the metric in the target, and you look at the 2, 0 part. So locally, it's P of Z dz squared. That's the 2, 0 part. And as we saw last week, this is holomorphic. So the phi, this locally is holomorphic, so it's actually a holomorphic quadratic differential. So this is a holomorphic quadratic differential. And so the theme here, which is really behind this theorem, is that the geometry of this Hopf differential tells us something about the asymptotic behavior of the harmonic map. Okay, so let me just quickly review that. This is something that Mike explained in his lecture already, but let me do this nonetheless. It's so the basic example to keep in mind is example 0, perhaps. It's the harmonic map between complex from the complex plane to hyperbolic to the plane, the hyperbolic plane, this two-dimensional hyperbolic space, which is defined as follows. So you collapse the complex plane to the real line along these vertical lines to the real line. So you can think of this as a map that just maps Z to its real part. And then you embed the real line as a geodesic isometrically. So it's an isometric embedding of the real line to H2. So this composition turns out is harmonic. This is also one of the first examples Mike gave in his talk. And its Hopf differential is a constant, where the constant something like 1/4. Right? And so here, so by geometry of the Hopf differential, I really mean the singular flat geometry. So it turns out that given a quadratic differential, holomorphic quadratic differential, one can look at, I'll write in locally, I look at the modulus of this fact, of this coefficient here, dz squared, that this defines a flat metric with singularities at the zeros of the Hopf differential. And so in this example, what happens is, and they are also, there's another feature of the geometry of this pair of foliations that are induced on the surface by the quadratic differential. Namely, there's this vertical foliation, which I've already drawn. So this is where the quadratic differential, these are the integral curves of directions in which the quadratic differential is real and negative. And there's also horizontal foliation where the quadratic differential, the directions are evaluated, the quadratic differentials evaluated in these directions give you positive real numbers. And for such a constant quadratic differential, these are precisely the horizontal and vertical lines, this picture. So if you look at this as also part of this geometry, so in this example, what happens is that horizontal leaves of the horizontal foliation, namely the horizontal lines, map isometrically under this map. So maybe it's up to a constant factor, which I'll just normalize, and I'll just assume that your maps isometrically, and the vertical leaves collapse, right? So this is what kind of happens in this example. And the key estimate, analytical estimate, this is sort of work of Wolf and Wan, and maybe I should also mention Han, Dam, Treibergs, and Wan, is that far away from the zeros, so far, in more general settings, so far from the zeros, again for maps to H2, I should add, so far from the zeros of the Hopf differential, the harmonic map sees this picture. Okay, and so what happens is that horizontal leaves map, I'll just write almost isometrically, and vertical leaves almost collapse, where almost here means, let me just quantify it a little bit. So almost means it's up to some additive error, which is exponentially small as you go away from the zeros. So here R is the distance from the zeros. The distance in this flat geometry, in this singular flat metric. So this distance from the zeros, and R is some sort of universal constant, positive. Okay, so this is the key estimate comes from analyzing these map to H2. So let me just actually, here, so this is a harmonic map. We are still to H2, and I should add that there's a fact proved, the work of my advisor, Yair Minsky, that this actually also holds, this estimate holds for maps to H2. So this holds, sorry, H3. So it holds for harmonic maps from the surface to H3, which is what's going to be relevant for us later on. Okay, but sticking to the maps to H2, so another example here which we've seen is that when you take the quadratic differential to have a pole, okay, so maybe a zero of order 1 at 0, it's a pole at infinity of order 5. So in this setting, you have this, the horizontal foliation has this kind of a threefold symmetry, as you can see by looking at this. And there is a harmonic map H from the complex plane to H2 with this prescribed hop differential. So with hop of H equals Q, this is sort of a result T2-1. This is where you can, for maps from complex plane to CH2, you can prescribe its hop differential. So then the image of this, by applying this estimate here, this lemma, would be an ideal triangle in hyperbolic plane. Okay, so as you go, these three sectors foliated by horizontal lines, as you go further away from the zero, these horizontal lines map close to one of the geodesics, and the line here will map close to these geodesic, and the sort of the vertical segment between these lines will sort of almost collapse, right? So this will be very small. And so as you go further out, these will be asymptotic to this ideal triangle. And so there's a theorem. So more generally, this was, again, example, but you can look at other polynomial quadratic differentials. And the theorem by Han, Tam, Freibergs, and Wan is that given an ideal polygon, let's call it P, there exists a harmonic map H from the complex plane to H2 that is asymptotic to P. Okay, and this has hop differential that looks like a polynomial dz squared. So this is a polynomial, in fact, of degree. If your ideal polygon has m ideal points, it has, we want the polynomial to have degree m minus 2. Okay. Now, if you're observant, you'll notice that it can't be a uniqueness here. It's not really a correspondence, simply because the dimensions don't match. So the space of ideal m-gons is real dimension m minus 3, because you can fix 3 of the points on the circle. But the space of polynomials of degree m minus 2, again up to automorphisms of the complex plane, is m minus 3 complex dimensions. Okay, so you have a mismatch of dimensions. In fact, so this is not unique in general, but there is a uniqueness statement that proved once you prescribe something. So it's a unique if one prescribes the principal part at the pole, part of the hop differential at the pole. Let me just say principal part at the pole. Okay, this is something I proved a few years back. Let me say what this is. So, well, as I kind of mentioned, this has a pole. This looks like at infinity, if you change coordinates, it will have a pole of order 5. So all these polynomial quadratic differentials has a pole of, if it's degree m minus 2, I think it is pole of order m plus 2. And the principal part is, if you look at the square root of the quadratic differential in these coordinates, you can, you look at the negative terms in the Laurent series of the square root of q in these coordinates. So this is a meromorphic form now. And so these negative terms sort of formally defines the principal part, okay? And it turns out that if you prescribe that, then these maps are unique. And this is where this uniqueness statement in this theorem also comes in. So we prove that, moreover, this U is unique if we prescribe, well, to be, okay, so I won't go into this, but there's something, there's a compatibility condition, but it's compatible principal. Okay, so so you can think of, this existence and uniqueness as a kind of as a warm-up to that theorem. And in fact, indeed, there is also another intermediate result, namely that it's known that so our theorem was proved for Fuchsian representation. So let me just mention that. In fact, it's going to be important for us. So the theorem, a recent result of Allegretti, which builds on sort of earlier work of Nathaniel Sagman and myself also, is that there is a homeomorphism between enhanced Teichmuller space and the space of meromorphic quadratic differentials on this X hat with prescribed principal paths. That's what I denote by the subscript P. So you prescribed principal paths. So, okay, so this, you can think of, so this is this homeomorphism via harmonic maps. And you can, this is a generalization of, or an analog of a theorem of Mike Wolf and Hitchin in the 80s, which parameterized the Teichmuller space of a closed surface with holomorphic quadratic differentials. So this is a kind of analog of that. And this is like a special case of a theorem where your representation is actually PSL 2R, and it's a Fuchsian representation. But we will use it. So let me, in the remaining time, give an idea of the proof of our result. So, let me see. So let me, this here, yes. Yeah. Yeah, right. There's a number of zeros. Well, okay, so if, yeah, so in principle here, this could be anything for this lemma. Okay, it's only, it's a, yeah, so X can be any surface, any Riemann surface for this, at least for this lemma, right? But when we're applying it here, it's the complex plane. And there, when we look at polynomial differentials, of course, there are only finitely many zeros. But I think this works more generally. Sorry. Yeah, that will be the sort of the distance from the zero set. So I guess it's harder to achieve if there are many zeros, right? So let me give an idea of the proof. So as I've told you, this sort of the technique would involve the harmonic map heat flow, which is in fact different from this prior work of either HTTW or Allegretti. And the sort of the difficulty is now the domain is also non-compact, not just the target. So anyway, so let me just quickly tell you the steps. One has to construct an initial map, U0. You have to run the harmonic map heat flow. And we have to prove the convergence to a harmonic map. And show that it's the desired map, the asymptotic to our beta. So I won't say much about the second step. This is where the analysis lies, but we rely on results about that extend, Eales and Sampson to non-compact domains and targets. So in particular, there's this theorem of Chiaping-Wang from the 1990s that builds on work of Li and Tam, which says that if your Mn are complete Riemannian manifolds, non-compact, and N is still non-positively curved, then if you have an initial map, a long-time solution to the harmonic map heat flow exists, provided if the tension field of this initial map is uniformly bounded, so it's L infinity N. Okay, so well, this is a simplified version of what he proves. And so to get started, at least to do step 2, we'll need to construct. So in step 1, we need an initial map from this universal cover to H3, which is, first of all, it's rho equivariant. And it is asymptotic to a desired framing, this beta. And we need this tension field, not too bad, so it's bounded. In fact, for step 3, it turns out we need something more, and we get that, so we'll say that later. So let me give an idea. So this is sort of the geometric part, step where we look at the geometry of H3. I'll give a quick idea of how this construction works. So it turns out that there exists a Fuchsian representation, rho naught PSL2R, such that our desired representation rho is obtained by bending rho naught. Okay, and I won't describe what bending means precisely, but let me draw a picture. So here's H3 again, and a totally geodesic copy of H2, namely the equatorial plane that I've drawn here. And a Fuchsian representation, or the image of this representation, will act preserving this equatorial plane, and it'll act very nicely on this plane. There will be a fundamental domain, like had before. And this is what a Fuchsian representation would look like. And if we bend this picture along geodesic lines lying in the equatorial plane, you can think of them as, again, as edges of ideal triangulation, if you like. Then this totally geodesic copy of H2 becomes a piecewise totally geodesic plane inside H3. So sort of roughly draw here a cartoon of it. Like this. This is what is called a pleated plane. This is one of the notions introduced by Thurston in his work on ends of hyperbolic 3 manifolds. And there'll be a new representation this time to PSL2C that acts preserving this bent object, this pleated plane. All right, and so what I'm saying here is that in our setup where our rows are non-degenerate, so it means that there exists an ideal triangulation with these complex cross ratios. You can make these cross ratios real and positive just by taking its modulus, and you get this Fuchsian representation. And so what we do is we actually start with the picture on the left. We start with a rho naught equivariant harmonic map from, let's call it H, from universal cover to H2, which is sitting inside H3 as a totally geodesic subspace. This exists by this theorem of Allegretti that I just mentioned. And we modify this to obtain our U naught. So we start with a map to this totally geodesic picture, but we really want something which is rho equivariant and asymptotic to this framing given by this the picture here. And so we kind of, so roughly speaking, we have to sort of bend that map to obtain our desired map U naught. And we can actually do this keeping this tension field bounded. So now this new map is no longer harmonic after this bending, but its tension field is bounded, and not only that, this has exponential decay, as if you think of it in the quotient punctured surface. Okay, so it is an invariant function at descends to the surface, and it has an exponential decay. And that's going to be important for step 3. So let me give a little bit of an remaining time idea of the last step of convergence, where again we have the issue that we need to show that one-point convergence. You want to need to show that at least one point converges, right? So a one-point convergence result. So this time, this belongs to some compact set. So this time we use the fact that, well, first of all, the energy density bound, which I didn't mention, but in step 2, we also have to prove that the energy density remains bounded and so on. So there's an energy density, uniform energy density bound that would prove that just like before, that this translation distance is bounded. And this implies that ut of x naught belongs to some neighborhood of the axis of rho of gamma. So here we are kind of using the fact that we are in a rank 1 symmetric space. As H3 has this property. If you look at it, so here I'm assuming that gamma is semi-simple. There's this axis. And if you take a point ut of x naught far from the axis, its translation distance by rho of gamma would blow up to infinity. So, but the energy density bound tells us that it doesn't. So there is a kind of a neighborhood where you're trapped. And moreover, if you're sort of non-degenerate, you have plenty of such semi-simple elements with distinct axes. Okay, so that's a fact. So this implies it's an analog of non-elementary. Also implies that there are elements in the image of rho with distinct axes. So in particular, I mean, this ut of x naught might be sort of, it must be kind of, if let's say there's another axis like this, another neighborhood, it must belong to the intersection of both these neighborhoods. And that's compact. Okay, so if it's non-empty, it has to be compact. So let me just say this. And then this intersection, so this is a we're kind of using the geometry of hyperbolic 3 space a bit. Okay, and then so this is how one traps points in a compact set, but we are not done because we still have to prove that it converges to the desired map. So it's kind of so that's asymptotic to beta. So this is some sort of a fourth step, which, and for this, we actually prove that the distance from the initial map is uniformly bounded. In fact, along the flow, it remains bounded. And so this uses, again, an analytic argument involving or at least a version of the parabolic maximum principle. Okay, so the distance function along from u0 to ut is not a subsolution, but of the heat equation, but it's so we can't directly apply the parabolic maximum principle in this non-compact setting. However, there is an inequality that looks like this, but here we use the fact that this has exponential decay, and that helps us. Okay, so there's a version of the parabolic maximum principle that we can prove for functions like this, and that's how we get this uniform boundedness along the flow. All right, okay, so I'm out of time, so stop here. Thanks.
Yes, thank you for the very nice talk. So questions?
Yeah.
Harmonic map, you can construct the connect.
Yes, that's right. So these are, okay, so I forgot to mention, so these harmonic maps with higher order poles of Hopf differentials also appear in the context of wild non-abelian Hodge correspondence. So there's a construction of harmonic metrics near the poles there. So this should be the same. So, but I mean, here we see it more geometrically. We see the asymptotic behavior of the harmonic maps in the symmetric space in H3 in this case more clearly, which I don't know whether one can glean that from the wild literature.
In that analytic has been done for harmonic independence, and because here are higher order poles, they allow only a pole of order 1, right?
No, but the work of Bickard and Bolch and then.
No, not beyond 1.
Okay. All right, then I could be wrong. So.
That's the maximum.
Yes, Mochizuki's work, yes. Okay, I thought that they did, but yeah, I might be.
But yeah, general context.
General. Yes, that's right. Yeah, so this is only SL2C, but of course one can ask what happens in SLNC. And so the analytic step of running the harmonic map heat flow is fine because there's theorems of the existence of long-time solutions work for non-positive curvature targets. But our construction, as we saw of the initial map, is kind of relies on the geometry of H3, and so, but there's possibly a generalization of that to rank symmetric spaces. I see. Okay, yeah, maybe we can discuss that.
Further questions? Charles?
Yeah.
So instead of doing SLNC, what happens if you do SO for one then? So an H4, let's say. So
Right. So
I mean, I see a couple steps where you don't have the Minsky estimates.
right. Yes, but that should work, I would guess. Okay. So I mean, there should be an analog of that for these estimates in H4.
But everything else seems to work, right? I mean,
Yeah, it should work in that.
non-compact.
That's right. Yeah, it should work.
And then I guess you need some other synthetic construction because maybe you have higher codimension that maybe bending is not, or maybe you can get away with also just bending or.
Right. I would expect you can still sort of, as far as 4 points are concerned, you can live in a copy of H3 and do this bending.
We do everything in a copy of H3.
Yeah. So it's at least locally, these well, in the construction, we really care about adjacent triangles.
But you don't want your
bent
you might
picture.
not want your map to just live in.
No,
you
but
just
adjacent
starting
triangles
map
would
lives in.
be.
Pardon?
So sort of, if you look at 4 points, they might live always in the boundary at infinity of H3. So sort of successive pairs
for
of
each
ideal triangles, you
Yeah,
can
yeah.
sort of do the construction locally as if you're in H3 and then
I see.
patch up. That would be my guess. Yeah.
Yeah, we could talk more.
Yeah, sure. Yeah.
So, what is the advantage of starting with this particular U0?
Also, it is close enough to being harmonic. So we started with the harmonic map here and did some bending, and there's an exponential decay that we need finally of the tension field. So tension field 0 is harmonic, but so this is not harmonic, but it is close to that. And we need that exponential decay somehow in that last step where we're wanting to apply.
But
parabolic.
other initial
Yeah, so
surfaces
there
could have
should be
also-
many ways of constructing that. I agree. So, but this is one such way.
Any further questions? Well, if not, then let's thank Subhojoy again for his nice talk.